if you would recall, we spent a couple days talking about the dot product. The thinking behind dot product is we are doing multiplication at an angle. If u and v, if the vectors all line up, this is what happens with scalars, because scalars don't have direction, so they kind of like always line up. But when vectors don't line up, we get some fraction of the magnitude. We get some fraction of the magnitude. A lot of times we'll think of it as some fraction of u gets multiplied by v, or some fraction of v gets multiplied by u. And the fraction that we get is the cosine of the angle, because we're making a multiplication, and the angle, the theta is, u and v are both adjacent to that angle theta, so it makes sense that we're using cosine. This multiplication at an angle is the same one that we use in physics when we break a vector into horizontal and vertical components. The goal here is to generalize breaking into horizontal and vertical components. We want to take a vector u and write it as a sum of a vector parallel to v and a vector perpendicular to v. For that, we need to multiply at an angle, and for that, we need the dot product. The cool thing about the dot product is that the dot product works in any space. So the dot product is always in effect, and it works in any Rn. Dot product is always in effect, and the dot product works in Rn. Cross product is a little bit more specialized. Cross product is we have a vector multiplied by another vector, and we get a vector. All of our thinking around the cross product is going to restrict it to R3. So the cross product is going to be specialized for R3. Our cross product is going to be an R3 thing. Dot product, more general, works everywhere, means the same thing everywhere. Cross product is going to be an R3 thing. Let's talk about the big idea of the cross product. The big idea is that the cross product is a vector perpendicular to both of the factor vectors. The cross product is perpendicular to both factors. So the cross product u cross v is perpendicular to u and perpendicular to v. Cross product will be like will create a normal vector. So the cross product will be normal to the plane containing u and v. The cross product is normal to the plane containing u and v. Once we say something like plane containing u and v, I must be talking about a plane defined by u, that can be defined by u and v, so we don't want u and v to be collinear. Then the calculation doesn't tell us really what we want it to tell us, because we're not, then we wouldn't be looking for a vector. Because if I got u and I got v, and they're not collinear, I'm defining a whole plane, and I can have one vector in R3 that is perpendicular to that plane. I can have one normal vector. But if I've got just one vector, if u and v are all just one vector, then perpendicular to that vector is an entire plane in R3. So visually, u cross v is perpendicular to the vector u and perpendicular to the vector v. It's normal, scroll. It's normal to the plane containing u and v. One thing you might want to notice is that if we have a plane, there's not just one vector that's normal. There's there's an uncountable infinity of vectors that are normal to the plane. But I also pointed my normal vector up away from the plane. But there's another direction that is also normal to the plane that's facing the other direction. So let's get into the calculation for u cross v and see what those two directions have in common, where they come from. Let's talk about how to calculate u cross v. So u cross v, the cross product of two vectors is the determinant of a matrix, but a very specific matrix. So on the top row of our matrix, we have I, j, and k. The second row will have u1, u2, and u3. That's where we'll put the first vector. And then along the bottom row, we'll put the second vector, v1, v2, and v3. Where, as expected, u is the vector u1, u2, u3, and v is the vector v1, v2, v3. So we'll calculate the dot product as this determinant. We can see that since we have I, j, k as entries in this matrix, we're going to have terms for I, j, and k. Because we know that that's going to happen, the most efficient thing to do is to use cofactor expansion across the first row. So we're going to calculate this using cofactor expansion along the first row. We're going to use cofactor expansion along the first row to calculate this determinant. Notice that u1, u2, and u3 are all scalars. They're the components of the vector u. So u is the vector u1, u2, u3. U is the vector. Its components are u1, u2, and u3. So u1, u2, and u3 are scalars. Similarly, v1, v2, and v3 are scalars. Cofactor expansion along the first row. So let's do that calculation. The first thing we need to do is when you have a matrix and you want to find the determinant, the cofactor of an entry is you take out the row, the column, and the row containing that entry. And what's left is the cofactor. So we're going to have the determinant of that. So this determinant will be, if we take out the column and the row containing I, we'll have the determinant of U2, U3, V2, V3. So I want the determinant of U2, U3, V2, V3. Oh yeah, I'm not trying to do secret math. So we take out the row and column, and whatever's left is the cofactor. So this is the cofactor for this first row, first column. Then we do the same thing. We make a cofactor for the J column, and that's going to have U1, U3, V1, V3. We'll get to that one, that part. And then our third term is for the K entry, and the cofactor for the K entry is U1, U2, V1, V2. The other thing that we have to remember, this cross product building works in R3, and I think R3 is so weird, even though that's like the one that we perceive, because anyway, R3 does weird shit. So we have to remember all kinds of weird shit. So when we're calculating a determinant, we have to remember that there's an alternating pattern to the signs. So it's not just add all these things up. There's an alternating pattern to the signs where first row, first column is a positive term. First row, second column is a negative term. First row, third column is a positive term. Now, if we happen to do the expansion down the first column, the first row, first column is positive. First row, first column, second row is negative, and then positive, and then positive and negative, and then negative and then positive. There's this alternating sign pattern when you're calculating a determinant. So we take our 3x3 determinant, and we're going to calculate it in terms of 2x2 determinants. Now we can calculate each of these cofactors. And these are the determinants where we go U2 times V3 minus U3 times V2. Spelled U wrong. This cofactor expansion is the same thing that we did in the previous one. I have this first row, first column U2, so I take out that row and that column, and I multiply U2 by the cofactor, which is V3. Then I go to the next row is U3, and I take out the column and the row containing U3, and the cofactor is V2. So I do U2 times V3, we alternate signs, so minus U3 times V2. Next up, and this term is positive. Next up, we're subtracting because we're calculating the determinant of this 3x3 matrix, and we have to alternate signs. And now we're going to multiply out this cofactor. And we do the same thing. Take out the row. I'm going to expand along the first row. So U1 gets multiplied by its cofactor, which is just V3, minus U3 times its cofactor V1. and that's my J coefficient. And then doing the same thing, U1 times the cofactor V2 minus U2 times the cofactor V1. At this point, we are looking at a vector, because remember, U1, U2, and U3, and V1, V2, and V3 are all scalars. So all my coefficients are scalars. Yes, the sign part is just knowing how the signs of our cofactors. So it starts off positive in the upper left. Then as we go across the row, we have to alternate signs. If there were 4 by 4, then it'd be plus minus plus minus. So we just alternate signs. If it was a 4 by 4 matrix, then each of these cofactors, there would be 4 terms, and each cofactor would be a 3 by 3. And then each 3 by 3 would be 3 2 by 2s. Yeah. So, and if it was 5 by 5, then your teacher's just being a dick. Or secretly wants you to jump onto Wolfram Alpha or some other determinant calculator. Question? You've got to remember how things are put together. It's all patterns. I don't want you to sit down and memorize this. Yeah. Yeah, this is the alternating pattern. So I don't want you to have to memorize this. I do want you to remember this, but I don't want you to memorize it. There's a lot of pattern going on. So this is the way that I tend to write it. I do alphabetical order. I go 2 3 3 2 1 3 3 1 1 2 2 1. There's also another common way would be to go U2 V3 minus V2 U3. Do you like alphabetical order or do you like numerical order? That's really just how you want to remember things. Also remember that I is with a 1. It's in that first column. So notice the subscripts are not 1s. In the J, I might write this 1 3 1 3. So this is a cofactor expansion across the first row. So it's usually shortcutted as AD minus BC. So most often when we see the determinant of a 2 by 2 matrix, but never heard of determinant? It's okay. It can be new. So the determinant is it's a number that we assign to square matrices that tells us something about that matrix, depending on what we happen to be doing at the time. So what we need to know right now is that we can use the determinant of a matrix to find the cross product of the matrix, because we do care about finding a vector perpendicular to 2 other vectors. So what we're looking at is a determinant. For our purposes, this is just a function that assigns to square matrices a real number. So this is just a function that takes a square matrix and assigns it a real number. We're using the determinant for our purposes because we're trying to find the cross product. We're using the determinant to find a vector because we're stopping the calculation because we're throwing in these vector terms. When you read about this in the book does the calculation, then it kind of goes straight to, it goes to this, the cross product written out with all the components. And most books distribute this negative, which really bothers me because there's like a pattern. There's a 2, 3, 2, 3, 1, 3, 1, 3, 1, 2, 1, 2. And it always starts with the first one. So if you distribute the negative, it disrupts the pattern, and I don't like it. So be it. Yes. Yeah, inside because we're alternating. Remember, in a cross product, in a determinant, we always alternate signs. So if we're expanding across the first row, it's plus minus. Yeah. If it was a 3 by 3, then it'd be plus minus plus. Wherever if we started on plus. If it's 3 by 2, we can't find the determinant because 3 by 2 would not be a square matrix. Determinant is a thing that we only do on a square matrix. So the reason that we care about the normal vector is that when we have a surface, we want to be able to describe the surface with just one vector. I'm sorry, what? Oh, the length will tell us some stuff about the area, about how curvy the surface is. One of the things that we can calculate. We have to get to that. Right now, all we care about is that we can describe a plane with one vector by using the normal vector. We got to think about what the calculus stuff that we're going to be doing with this as well. Because right now we're finding the normal vector to a plane, but not all surfaces are planes. But remember that a plane is a linear function. And so it's going to hold the same place that a linear function in R2 has. In Calc 1, we spent a lot of time finding the slope of the line tangent to a curve at a given point. The Calc 3 version of that question is, what is the plane tangent to a surface at a given point? That's just taking everything up one dimension. Instead of slope of the line tangent to a curve at a given point, we're going to find the equation of a plane tangent to a surface at a given point. We're going to want to describe that plane with one vector, and that vector will be the normal vector. So it's going to be important to figure out what that normal vector is in relation to a plane, because all surfaces are just a bunch of planes. Just like all curves are just a bunch of line segments. Partly, we're not so much describing how like a vector would react to the surface of a mirror. We're just describing the surface itself. Because when something comes along and hits the surface, we have to be able to describe what kind of angle is something coming in and hitting that surface. Like if I come in, am I coming in directly at the surface, or am I coming in at an angle? What does it mean to come at an angle if our surface is curved? I need like a curved surface. I'll have one. What does it mean to come at the surface at an angle? What angle are we coming at? And what we'll do is we'll describe this curved surface. We'll look at the point where the impact happens, and we'll put a tangent plane there. And that's how we can describe the angle where things are happening. That's how we'll describe That's how we'll describe the surface, essentially with a tangent plane and a vector normal to that plane. Yes. Yeah. And so that place where the ball hits the curved surface, if we think of the ball, if the ball is only going to hit it at a point because we're going to simplify everything, then that surface is going to be flat. We have to be able to describe that flat part of the surface. As long as the surface is continuous. That goes back to a Calc 1 idea. If something is continuous and you look close enough, it'll look flat. When you look close enough at a curved surface, it always looks flat, continuous. Sure. So we need to be able to make this calculation. So we're also going to need to figure out how to make Wolfram Alpha tell us what this calculation is, because it will, because it's our favorite calculator. It's actually not our favorite calculator. It's very good at very many things, but like when you're in your linear algebra class, it's kind of better to have the 90s technology of the TI-84, because you can find the reduced echelon form of a matrix right from the front of the calculator. You don't have to do anything fancy. But the TI-84, even though described as a graphing calculator, is absolute shit for graphing. Desmos is a better graphing calculator. So this is the cross product. This is how we will calculate, given two vectors, a vector perpendicular to both those vectors. Sorry, but okay. Remember what we're trying to do. We're trying to expand on this problem. We have a curve. Our old problem was find a slope of a line tangent to the curve. More like we describe, instead of describing using this curve, we simplify the curve by thinking about the tangent line. We use the tangent line to approximate the curve. In Calc 3, this curve is no longer a curve. This curve is inconveniently a surface. So we upgrade our tangent line to a tangent plane. In the line, because of the kind of poor decisions we made when we were setting up algebra, we decided to use the slope of the line to determine the direction. But if this is a tangent plane, I can't use slope because there are two of them. There's a slope in the y direction, there's a slope in the x direction. But what we can do is describe the direction of this tangent plane with a normal vector. So this is what we need to calculate. We need to be able to calculate a vector perpendicular to two vectors. It's this somewhat messy determinant calculation. It's mostly messy because we're writing it all out in general. Also, not everybody comes into Calc 3 by way of linear algebra after Calc 2. Let's do an example. I think the traditional thing to do now is to calculate a cross product. Problem is, it's hard to draw because It's in R3. So let's do an example. I need a vector u, and it needs to come from R3. So let's do 5, -3, 1, and let's have a vector v. Almost spelled v wrong. Now the calculation looks like it involves a lot of writing, but it doesn't. Remember all the writing in a math class where it's at where you're supposed to show your work. I think we need to emphasize the show your work aspect of that. Because the point of being in a math class is to not have to write down all the math that your teacher says you need to write down. It's really kind of this weird signal. Like in algebra, it's like, I'll show all your steps. The point is to go from the start to the finish without having to write down all the steps. So if you're writing down less, that's a plus. But then you get marked down for that because your teacher doesn't trust you. And even as a child, you saw that. You're like, oh, you don't trust me. You don't think I know what I'm doing. Anyway, let's find u cross v. So u cross v, I need a vector perpendicular to these two vectors. It's going to be the determinant of the matrix. Across the top, we'll put I, j, and k. And my first row will be the first vector listed, 5, -3, 1. And the second row will be the second vector listed, 0, 4, 1. So first I need my I component. So if I take out the 5, 0, I'm left with -3, 1, 4, 1. So I need the determinant of -3, 1, 4, 1. So -3 times 1 is -3 minus 1 times 4 is 4. So -3 minus 4 is -7. I'll write down the details underneath. So for the J column, my cofactor is going to be 5, 1, 0, 1. So I'm taking out the second column. So I need the determinant of 5, 1, 0, 1. So 5 times 1 minus 1 times 0 is a 5. But since I'm doing cofactor expansion, I know I have to change the sign, so it's going to be a -5. It always sounds like a game of Fizbin, but then no one's seen original Star Trek, so they might not know what Fizbin is. It'd be like Calvin Ball, but Calvin and Hobbes ended a long time ago, so no one knows what Calvin and Hobbes is, and I don't know what the current zeitgeist says the mystery game should be. The last term would be 5, the cofactor would be 5, -3, 0, 4. So 5 times 4 is 20, minus -3 times 0. So we'll just have a plus 20k. So this vector, -7, -5, 20 is perpendicular to 5, -3, 1, and 0, 4, 1, assuming that I did the correct calculation, which is not a safe assumption to make because that's arithmetic, and I'm not very good at arithmetic. So here is a vector that is perpendicular to both u and v. So the -7 is the first term in the cofactor expansion. So the first term in the cofactor expansion will be the determinant of everything without the I column. Negative 3, 1, 4, 1. And so this is going to be negative 3 times 1 minus 1 times 4. And so there's our negative 7. So negative 3 minus 4, negative 7. Our next term is the J term. So our cofactor will be 5, 1, 0, 1. But we're doing a determinant, so we have to change the sign to a negative. Then the cofactor will be 5 times 1 minus 1 times 0. And then finally for the K term, we'll take out the K column and have 5, negative 3, 0, 4. And the determinant is going to be, of the 2 by 2, will be 5 times 4 minus negative 3 times 0. In the chat, it says, oh, okay, that makes sense. Incorrect. It doesn't make sense, but it is what we do. That's correct. It doesn't make sense, but this is what we do. It raises the question, why would we do it this way? Because it works. It does a thing that we want. And at this point, that's all we get to know. Sometimes math is annoying like that. Like, well, here's how you do a thing. And you're like, well, but why though? You'll find out later. And then we all just secretly hope you forget. Kind of everything. Then eventually you do find out why stuff works in math. But it usually just comes later on. That's why it's secretly a cop-out when you're a math student to be like, oh, but I really want to understand what's going on. Like, all decisions have been made as to what you get to understand. And sometimes you don't get to understand until later. It's a holdover from when our calculators were powered by humans. True. But remember, learning math is a function of time. And sometimes you want to get started on the mechanical bits so you can kind of internalize those mechanical bits before you move on to doing something deeper. It's the same as, it's the analogy I've used before. When you first start in physics, you start learning physics and you're ignoring things like air resistance and you're ignoring things like friction because it simplifies the problem. You start off with a simpler problem and then build in complication later. You don't start with the entire problem first and try to solve that. You start with a simpler problem and build out from there. And that's kind of what we've done here. Here's the thing that I want. I want a vector. I want a vector perpendicular to 2 given vectors. Here's how we can get it. How did someone figure this out? I don't know. It's one of those history of math things. If you want to find where the cross product, where determinants came from, I think the best course of action would be to go on to TikTok or YouTube and ask Hank Green. And he would probably be happy to explain it to you because he either probably knows or knows someone who does know. You know what I mean? One thing to note is that this vector should be perpendicular to both u and v, which means its dot product, the dot product of u dot oops. U cross V should be equal to 0. And the dot product of V dot U cross V should be equal to 0. Because U is supposed to be perpendicular. U cross V is supposed to be perpendicular to U and V. So if we have negative 35 plus 15 plus 20 is 0. And we have 0 minus 20 plus 20 is 0. So we can see that the dot product of these two dot products are equal to 0. So our cross product is in fact perpendicular to both U and V. Any questions? All right, so there's homework for chapter 13. 13 is just like vectors, then dot product, then cross product. Be able to find the cross product of a couple of vectors. More importantly, be able to interpret the cross product as a vector perpendicular to the two vectors that are factors. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.